Osculating circles. Suppose we form a circle in the osculating plane of C at point P on the curve. Assume that the circle has the same curvature as the curve does at point P and let the circle have the radius r. Then the curvature of the circle is given by 1 over r. We call r the radius of curvature of the curve, and it is equal to the reciprocal of the curvature. If this circle lies on the concave side of the curve and is tangent to the curve at point P, then this circle is called the osculating circle of C at P, as shown in the following figure. So if we look below at the figure down here, what we'll see here is we'll see that we have this point P here, and from this point P we have this tangent line, which if we find the tangent vector there, and we find the orthogonal vector to that, that's called the unit normal vector. Then what we can do from there, remember, if it's a unit normal vector or a unit tangent vector, that means they have length 1, then we can multiply the normal vector by r, which is the radius of curvature, which is defined by or equal to the reciprocal of the curvature. Then we can multiply it by that, and that'll take us right to the center of the osculating circle. And that's what we need here if we're going to set up the equation for that. So we'll need a center, and we'll also need r. So that's what we're going to do for this problem here. So take a look at the problem at hand. It says find the equation in terms of x and y of the osculating circle of the curvature defined by the vector valued function rt equals t squared I plus tj at t equals 1. So I'm going to write rt in component form. I always like component form for myself. If you don't use it, that's fine. Coming from physics, you probably like the i's and the j's, but this works for me. So I'm going to get the t squared t, and if I actually graph this, I'm going to turn this into rectangular so you can actually see what the graph will look like, and then it will make a little more sense, I think. So anyways, so the first component is my x, so x equals t squared, and y equals t. And if I actually plug in my t in for this for y here, then I'm going to get x equals y squared. And this is just a sideways parabola, and that's what we see here. So that graph looks like this. And from here, because we're dealing with t, we do have a direction on this curve here. It's just a sideways parabola. And we're actually going in this direction. So what that means for us, if we're looking at t equals 1, then t equals 1 means I'm going to be at the point 1, 1, because I essentially just plug in 1 for t here, and that will give me the point 1, 1. So really what we're doing is we're looking at this point here, and we're going to find the osculating circle for really x equals 1. So remember our procedure here. So that means we're first going to find a tangent vector, and it's going to go in that direction since my curve is going in that direction. And then once I find that tangent vector, I'm going to find the normal vector, and again, those are unit vectors. And then once I find that unit vector, I'm going to multiply it by the r, which is the reciprocal of the curvature, and that's going to extend it out, which will result in the center of that osculating circle. Having the center and the radius, then I will be able to write the equation for that osculating circle. So for us to start, we're going to find t. So the formula for t is t equals r prime t over the magnitude of r prime t. And that's going to be where we start. So if rt is t squared comma t, and I'm looking for r prime t, that's simply going to be 2t comma 1. So there's my r prime t. And then to take the magnitude of that, that means I'm going to take the square root. Let me write that down first. So that's going to be the square root of 2t squared plus 1 squared, which this is going to be the square root of 4t squared plus 1. And that's what the bottom's going to be here. So now, since I have t here, now we're going to talk about n, because now we're going to need our normal vector. And they call that a unit normal vector. So then my nt is going to be t prime t over the magnitude of t prime t. And that's where this is coming from. So it's the derivative, the second derivative of rt. So for t prime t, we're going to get equals, this is going to be a big parenthesis here. Two over, and we're going to get 4t squared plus 1, and that's going to be to the 3/2 power. And then for the second one, we're going to get negative 4t. Let me write that over a little bit so it looks better. Okay, so negative 4t, and that's going to be over 4t squared plus 1, and that's also to the 3/2 power. And that's going to be the t prime. Now for the bottom of this, it's going to be t prime t, magnitude. We're going to end up with 2 over, and that's going to be 4t squared plus 1. Now what we're going to have to do here with each of these components, so we have 2 in the top here, so each of these, like this 2 over 4t plus 1 to the 3/2 power, is going to have to be divided by 2 over 4t squared plus 1. So we're actually going to divide that here, and I just want to show you what that looks like. So if you remember how to divide with fractions, I take the first one, so I'm going to just write that out. And I'm going to take that second component, which is the bottom here, not really second component, but the bottom, and I'm going to multiply by its reciprocal, so I'm going to have 4t squared plus 1 on top now, and 2 on the bottom. So we can see that the 2's cancel, and I get 1's in place of those. And this 4t squared also cancels with, now remember I have 3/2 here, and this is like to the first power, which is really just 2 over 2. And if I'm canceling them out, it's going to subtract them, so it's going to take 2 of those, so that's going to end up being 4t squared plus 1 to the 1/2 power. And this cancels out and becomes a 1. So we end up with 1 over square root of 4t squared plus 1. And that's we end up with that first component. Similarly, we're going to deal with the second component. And again, I'm just going to write the top down. And I'm going to times that by the reciprocal of the bottom. So it's the same for the other one. So it's 4t squared plus 1 over, and then I have that 2 on the bottom. And I can see here that I have a 4 there, which that's going to become a 2. And don't leave the negative out. Don't forget about that. So those are going to cancel. And again, we get that same canceling here. So I'm going to end up with the square root on the bottom of that one as well. So this one's going to end up being negative 2 over square root of 4t squared plus 1. And that's going to be n for us there. And I almost forgot my t, which comes from this little piece here. So don't forget your t. Try not to forget anything there. It's easy to do. So that's going to be n. So there's our n. Now we need to find k here. So for curvature, that's going to be equal to the magnitude of t prime t over the magnitude of r prime t. So we had both of those already previously. Our t prime t was 2 over 4t squared plus 1, and that's going to be over r prime t, and r prime t, the magnitude here, is going to be the square root of 4t squared plus 1. So this is going to be the square root of 4t squared plus 1. So that's what that's going to be for curvature. I'm going to clean that up a little bit for sure. So since I have this rational expression on top, I'm going to have to do the same thing for the bottom. Now, it's not really a rational expression because it has the square root in it, but again, it has a similar property. So that I can think of this over 1. Now I'm going to have to flip that and multiply. So this is really going to be 2 over 4t squared plus 1 times 1 over the square root of 4t squared plus 1. And if I look at this, I can actually multiply those. This first one is the power of 1, which is really 2 over 2. And what do I generally do? I add my exponents when I'm multiplying with the same basis. So when I multiply the 4t squared plus 1 times the square root of 4t squared plus 1, which is really 4t squared plus 1 to the 1/2 power, and I add those exponents, that's going to be 4t squared plus 1 to the 3/2 power. And then 2 times 1 is just going to be 2. So there's our curvature. It's 2 over 4t squared plus 1 to the 3/2 power. So now what we need to do is we need to consider at what value we're talking about here. Now remember, it said t equals 1. So now what we have to do for each of these is just plug in t equals 1. Now we don't need the tangent, the unit tangent vector, but we're going to do that one anyways because I want to show you something here. So if I plug in 1 for that first one there, so t1, in essence what I'm doing here is I'm just plugging in 1 for every t. And what you'll see that we get here is that's going to be 2 times 1 here, so I get a 2 on top. And that's going to be 4 times 1 squared, which is just 4 plus 1 is 5. So I'm going to end up with 2 over root 5. And that's going to be the first piece. So 2 over square root of 5. And then for the second piece here, I'm going to plug in a 1 as well there. So that's going to be 1 over square root of 5 once you work all that out. And then for n1, so that's the next one, I'm going to plug in 1 for every t in those. So for the first one here, that's going to be 1 over 4 times 1 squared plus 1. So that's going to end up being 1 over the square root of 5. And then for the second piece here, I'm going to have that negative. Now again, I'm going to put a 1 there and a 1 there, so that's going to be negative 2 over the square root of 5. And this is what I wanted to show you about t and n. If you notice here, the first component here is actually going to be the second component negated in n. And if I look at the second component, that's actually going to be the first component of n. And that makes sense if you think about this. They're supposed to be orthogonal. Now remember that. Here's t, and here's n here. And they're orthogonal, which means their dot product is 0. So if I times 2 over square root of 5 times 1 over square root of 5, and I add that to negative 1 over square root of 5 times negative 2 over square root of 5, we can see that those are going to give us the same value, but opposite signs, so they're going to zero out when I add those together. So that should make sense where that comes from. So that's the idea, and I wanted to show that to you. So in most cases, I could just take the first term, move it to the second term, and negate it, and then take the second term and move it to the first, and then I have n, without doing all of those computations. Now again, I might have to change that by a sign depending if I'm facing inward. But if I work this out by hand, I'm always going to be facing inward in the curve, so I wouldn't have to contemplate which way I should go with that. So what I mean here is if this wasn't the right direction, like inside of the curve, like towards the inner curve, then I would have to negate it, so that would be a negative, and then that would be positive if I just thought about it that way. But anyways, either way, they're both normal vectors to t. That's something worth noting. So now let's talk about k then, because we want that k, that curvature as well. So that curvature then, I'm just going to plug in 1 for t as well here. And that's going to end up being 2 over square root of, not square root of 5, but 5 to the 3/2 power. So 2 over 5 to the 3/2 power. Now what we're going to do next is multiply that curvature. Well, first off, we have to find the radius. Okay, so let me do that. I'm getting a little ahead of myself there. That's 1 over the curvature. So that's going to end up being 5 to the 3/2 on top over 2. So remember, now that I have n, and that's a unit normal vector, that means it has length 1. And then I times it by r, that's going to extend it out far enough, so that's actually going to be the center of my circle when it's all said and done. So I'm going to take my curvature, which is 5 to the 3/2 power over 2, and I'm going to times that by that n1 there, which is 1 over the square root of 5, comma, negative 2 over the square root of 5. And I want you to notice something here. This square root of 5 on the bottom is really 5 to the 1/2. And I'm going to cancel that out with one of those. So that's really going to be 5 to the 2 over 2, which is really just 5. So I'm going to end up getting for that first piece 5/2. And then for that second piece, I'm going to do the same thing. I'm going to multiply it. And notice that 5 to the 1/2 power is going to cancel with one of those. So it's going to make that a 5 to the 2 over 2, just like the last one did, which is really just 5. So this is going to end up being 5. And when I multiply it times the negative 2, that's going to end up being negative 10. And then when I multiply the bottom, now remember when I cross that square root of 5 out, it's going to be 2 times 1. So that's going to be 2. So it's going to be negative 10 over 2, which when I reduce that is negative 5. So this is going to be that vector in the direction with the right length now of r, so that it'll be the center of that osculating circle. Now again, we need r and we need the center to write an equation for a circle. So I did the graph of this on the next page here, so take a look at this. Now just keep in mind here, we're going to put it all together in a second, and I want you to see this. So first we have the circle here. Not the circle, but the point, 1, 1, that's where we're starting at with this curve. And then I'm going to make the tangent vector, and that would be there. And then next we're going to have n, but I'm going to pick the n that also is multiplied by that r. And that's going to be this vector here. Now remember what it was. The vector was 5 over 2, comma, negative 5. So that means I'm going to go to the right 5/2. Now keep in mind here, every 2 notches is 1, so every notch is a half. So just keep that in mind. So this is going to be 1/2, 2/2, 3/2, 4/2, and 5/2. And then I'm going to go down negative 5. Or I should say down 5. So this is going to be 1, because this is at, remember, 1, 1 here. Okay, so I'm going to go down 1. So here's 1, 2, 3. Oops, did I miss one? I think I did. So 1, 2, 3, 4, and 5. That's down 5. And if I label that point there, now remember I'm starting at 1, 1. That point there is going to be 5/2 to the right, and I'm starting with a 1 here. So that's 2 over 2, and then I add 5/2 to that. That's going to be 7/2. And then for my y value, I'm starting at 1 here for the y value, and I'm going down 5, so that's going to put me at negative 4. So that point is going to be 7/2, negative 4. So there's our center. And the radius of this circle is, if we go back, the radius was 5 to the 3/2 power over 2, which when we clean this up is really going to be 5 cubed, and I'm going to square root it. So it's going to be the square root of 125 over 2, which gives us 5 square root 5 over 2 as our r. And then we have the center now, so we can just set up our equation. So it's x minus h, so that h now is going to be the horizontal, which is 7/2, because now I'm thinking about moving from the center, and that's going to be 7/2. And then I'm going to have the squared here plus y here, and it's going to shift down, and it's coming from the x now. It's going to shift down 4, so that's going to be a plus 4 squared, and that's going to equal my r squared here. So then if I square this 5 root 5 over 2, and I'll do that below here. When I square the 5, that's 25. When I square the square root of 5, that's 5. And when I square root 2, or square 2, excuse me, not square root, but square 2, that's going to give me 4. So that's really 25 times 5, so that's 125 over 4. So that's where we get the 125 over 4. So this is the answer for this problem. This is that osculating circle that we were looking for in terms of x and y. And looking at the picture there, we can clearly see that that's going to be the center of this circle, of this graph. That's what's really cool about this. But there's our answer we're looking for, and I wanted to give you the geometric description of it as well, just to hopefully give it a little more meaning for you. So when you think about those vectors of how this moves in the direction, it's always moving from that point of interest, which turned out to be 1, 1 for us here. So there's